Okay, so back to section 14.1. Now, remember, from calculus 1, let's say we are integrating the number 1 as an integrand on the interval AB. So the function 1. Well, in this case, of course, we take the antiderivative of 1, which is just x, and we plug in b and subtract off a, which is just b minus a. And of course, that's just the area of this rectangle. But it's also the length of the interval . It's the length of the interval, b minus a. So if we are integrate over a two-dimensional region R, and we integrate the function 1, so I'm about to introduce a new notation. Instead of putting like the inside limits of integration here and the outside limits of integration here, I'm just going to put R, and that means you have to arrange it to put the inside limits of integration and the outside limits of integration. We integrate the number 1. I'll put dy dx in here, even though I'm abusing notation a little bit because I shouldn't be using dy dx when I just have this R right here. Then what we have is the area of the region R. So when you integrate 1 over a region, you get the area of the region, just like when you integrate 1 over an interval, you get the length of the interval. Oops. Area of the region R. Now, what I really should have written over here instead of dy dx is the double integral over R of 1 d capital A. And this is sort of a shorthand notation for dy dx or dx dy. Now, we did this integrated integral business yesterday. Sometimes it is easier to integrate with y on the inside and x on the outside, and sometimes it's easier to integrate with x on the inside and y on the outside. Let me give you an example of why that might be true. So let's say we have a region which looks like this. So here's my region. Let's say here's 1, 2, 3, 1, 2, 3. And let's go ahead and put a dot here at 1, 1, a dot at 2, 2, a dot at 3, 2, and a dot at 2, 1. So we make this parallelogram. So this is my region R, the interior of that parallelogram. And let's say we want to integrate something, some function over this region R. Due to the region, it's almost certainly going to be easier in one direction than it is other. Now, it partly depends on what the integrand is, because some integrands are easier if you do them dy dx, and some integrands are easier if you do them dx dy. And a lot of times it doesn't make any difference at all with the integrand. But let's see why this might be easier doing x on the inside and y on the outside. If we do this x on the inside and y on the outside, so we could very easily evaluate this as, so I'll leave a little bit more space between my integral symbols. Now we'll do x on the inside and y on the outside. Now the outside one, remember, we always have numbers here and here. So we'll go from the minimum y to the maximum y. So when the minimum y is 1, the maximum y is 2. So we're going to go from 1 to 2. And if you're doing dx on the inside, you're going from the left curve to the right curve. So this is going to be x equals something in terms of y and x equals something in terms of y. The inside limits of integration can use the outside variable. So let's figure out what these two curves are, these two straight lines. Well, this straight line just is y equals x. We need it as x equals something in y. If y equals x, then x equals y. So we're going from y, so the left boundary, to the right boundary. Well, this line is y equals x minus 1. And so if we get x by itself, it's x equals y plus 1. So we're going from y to y plus 1. And then we just do our integration. We'll take the antiderivative with respect to y, plug in x equals y plus 1, and subtract off what we get when x equals y. Let's actually do this with a specific example. So let's say we have, let's say f of xy equals, so let's just say xy. So what we're integrating here, what we're integrating here is from 1 to 2, and from y to y plus 1, xy, we're doing x on the inside and y on the outside. Again, I emphasize that on the outside, we always have just numbers here, but on the inside, we can have the outside variable. So the first thing we're going to do is take the antiderivative with respect to x. So this is, we take the antiderivative with respect to x, we're going to have 1/2 x squared y. We're going to go from x equals y to x equals y plus 1. I highly recommend not just writing y and y plus 1 here, writing x equals, just because there's so many variables floating around, and pretty soon when we start doing triple integration, we're going to have yet another variable floating around. So please keep everything straight. X equals y plus 1, rather than just y to y plus 1, because then it's not 100% clear where that y goes. So 1 to 2. We're going to plug in the y plus 1. So we have 1/2 y plus 1 squared times y minus 1/2 y squared times y dy. We can multiply all this out. So we have what, y squared, y cubed, so 1/2 y cubed. So plus 2y squared, so that's plus y squared plus y, so 1/2 y minus 1/2 y cubed dy. So we have 1/2 y cubed minus 1/2 y cubed. I guess they cancel. So we're just left with y squared plus 1/2 y dy. And after that, you could give this to any old Calculus 1 student and they'd be able to do it. So I'm just going to leave it at that point. Okay. So we said this was going to be easier doing X on the inside and Y on the outside rather than doing X on the outside and Y on the inside. Let's see why. Let's see what happens if we try to do X on the outside and Y on the inside. So what we've just done with X on the inside is integrated this in horizontal stripes, going from the left boundary to the right boundary. So let's try this, where we're going to integrate from the bottom to the top. So Y on the inside and X on the outside. Now, what we're doing is we're integrating from the bottom curve to the top curve. The problem is the bottom curve changes at 2. It changes from Y equals 1 to Y equals X minus 1. And the top curve also changes at 2. So we're going from, so between 1 and 2, the top curve is Y equals X. And then after 2, it's Y equals 2. So we actually have to do this as the sum of 2 integrals. So let me move over just a little bit. I think you can still see it on the screen. So we have to do this as the sum of 2 integrals. We're going to break this into 2 triangles. So let's see, we did dy on the inside and x on the outside here. And we have one more integral to do. Again, with y on the inside and x on the outside. So we're going to do this left-hand triangle and the right-hand triangle. In the left-hand triangle, x goes between 1 and 2. The outside numbers are always, the outside limits of integration are always numbers. Now the inside, we're going to go from the bottom curve to the top curve. The bottom curve is y equals 1, and the top curve is y equals x. And then we'll put our integrand. I'll use that same integrand over there. I'll use xy. And now we'll do the right-hand triangle. So here the bottom curve is y equals x minus 1. And the top limit of integration is y equals 2. That line is y equals 2. And of course, the outside limits, we're going from 2 to 3. X goes from 2 to 3. So xy. So it's a little bit more difficult here, not because of the integrand, but because we had to break this region up into 2 to do y on the inside and x on the outside. We're doing it in vertical stripes now, because when you do y on the inside and x on the outside, you take the top curve and subtract off the bottom curve for your inside limits of integration. And the top curve changes at 2. It changes from y equals x to y equals 2. And of course, the bottom curve also changes to y equals 2. So this one I think is definitely easier if we do horizontal stripes with x on the inside and y on the outside. Okay, let's see. I guess that more or less polishes off section 14.1. Now on to section 14.2. This is also a generalization of what we've done in Calculus 1. And I sort of mentioned this yesterday, silently, in response to a question. So multiple integration. Oh, wait a minute, double integrals in volume. Double integrals in volume. So again, recall from Calculus 1, if a function is at least as big as 0 on an interval AB, so in other words, the curve is completely above the x-axis on the interval AB, then the integral from a to b of f of x dx can be interpreted as the area of A. So here's the region A. Likewise, if y is positive, or at least non-negative, on a region R in R2 in the XY plane. So in other words, we have this region R in the plane, and the surface Z equals XY. If this surface is entirely above the XY plane, at least over top of R, then we can interpret the double integral over R of f of xy dA as the volume of this region right here. Now, back in calculus 1, we know that stuff below the x-axis counts as negative area. We know that the integration is really signed area when we have a single real variable. So if I have something like this, stuff below the x-axis counts as negative area. So if this is A1 and this is A2, then, and this curve is y equals f of x, then the integral from A to B of f of x dx is the area of A1 minus the area of A2. Anything below the x-axis counts as negative area. And it works the same over here. Anything below the sea level counts as negative volume. So it's, I don't know if there's too much that I have to say about that, but just like integral actually stands for the concept of signed area, we can interpret it as the concept of signed area, plus and minus. Double integral, we can interpret that as signed volume, where stuff below the x-axis counts as negative volume. Okay. There's more I could say, but I think these videos are best kept short. So that's all I'll do today, and we are more or less caught up, and we'll just do some more practice when I get back on Monday. So have a good weekend, everybody, and I'll talk to you soon.